Escape rooms are the ultimate test of collaboration, deduction, and lateral thinking. But what happens when the confines of the room expand to encompass the entire globe? We are exploring how Google Maps, the single most comprehensive geographic information system available to the public, can be transformed from a simple navigation tool into a complex, multi-layered escape room puzzle generator. This requires leveraging features often overlooked: metadata, historical archives, complex pathfinding algorithms, and user-generated content. The power of Google Maps lies not just in showing you where you are, but in providing dozens of simultaneous data points that, when filtered correctly, hide the keys to your freedom. Get ready to dive deep into digital cartography and geographical sleuthing, proving that sometimes the biggest lock is hidden in plain sight on a satellite image. To understand the puzzles, we must acknowledge the foundation. Google Maps officially launched on February 8, 2005, primarily focused on desktop users, revolutionizing how we interact with geography. Initially, it offered basic routing and satellite imagery. However, the game changed drastically 2 years later, in May 2007, with the introduction of Street View, starting in just 5 U.S. cities. Every puzzle we design relies on one of these core data streams, whether it's the static, high-resolution satellite photography, the ground-level perspective of Street View, or the underlying mathematical structure of latitude and longitude. Accuracy in these historical facts is crucial, as some puzzles demand players to interact with the map as it existed in a specific temporal state, forcing them to understand the map's evolution. The core mechanical challenge of a maps-based escape room is linking the digital discovery to a physical lock. Every successful decryption on the screen must yield a numerical, alphabetical, or symbolic key that can be used on a physical prop, such as a directional padlock, a cipher disk, or a key safe. This is where clever design comes in. For example, the precise altitude of a digital landmark might correspond to the depth setting on a physical antique scale, or the number of stars on a business review could dictate the order of colored wires to cut. The complexity ensures that players cannot simply brute force the answer. They must prove their geographical deduction to move forward. This constant tension between digital space and physical constraint is the engine driving our 12 unique ideas. Before tackling the puzzles, players need the rules: access to a dedicated computer terminal, reliable internet, and the constraint that all answers must originate from verifiable data within Google Maps, or closely integrated systems like What3Words. Puzzles often involve specific map layers, simple searches, and maximizing complex data extraction. The clues given in the physical room will never reveal the answer directly, only the coordinates, landmark names, or specific parameters needed to perform the required geographical calculation. Precision is paramount. 1 decimal place off and the physical lock won't click open. Our first puzzle, the geocache latitude lock, capitalizes on the mathematics of location. The team finds 3 small physical tokens in the room, each inscribed with incomplete coordinates, perhaps missing the minutes and seconds for a specific degree of latitude or longitude. The accompanying paper clue provides the exact calculation required, such as find the distance in kilometers between point A and point B, then divide that distance by the square root of point C's total degrees of latitude. This requires players to first find the precise coordinates of 3 specific minor landmarks hidden on the map, often small parks or obscure monuments, testing their ability to accurately read the digital GPS data displayed by the tool. Once the required coordinates are determined, the players must execute the mathematical formula provided. The result of this complex calculation, perhaps 8.54 kilometers, must then be translated into the key. The escape room utilizes a specific format, instructing the players to use only the whole number and the first 2 decimal places, yielding 854. This number is the combination for a small lockbox containing the next stage of physical clues. This puzzle ensures that players are proficient not only in using the measurement tools built into maps, but also in manipulating and rounding geographical data precisely to unlock a tangible reward. The Street View Time Warp uses the archive feature, a treasure trove of chronological data. The physical room contains a faded photograph of a building taken 10 years ago, alongside a current street address. The players navigate Street View to that address and activate the See More Dates option, scrolling back through the archive. The challenge lies in finding a specific minor structural change between two distinct timestamps. Perhaps in the 2012 view, a specific blue dumpster is visible, but in the 2017 view, it is replaced by a green recycling bin. The years 2012 and 2017 are the first two numerical digits of the code, but the players must prove their observation skills by finding the hidden object. The puzzle deepens. The players now know the change occurred between 2012 and 2017. The solution requires them to find a final clue visible only in one of the archived views, perhaps a barely visible partial phone number spray-painted on a temporary construction barrier in the 2015 image, an image they might skip if they only check the earliest and latest dates. The digits 555 are part of the phone number. When combined with the year dates found previously, the final code is 2015-555. This forces methodical examination of every available Street View snapshot, testing patience and attention to micro details within the digital environment. The Pegman persona lock utilizes the iconic yellow avatar that initiates Street View. Pegman's color changes based on the data available at the coordinates where he is dropped. Usually yellow, he might turn green when exploring national parks or blue when accessing interior views of museums. The team is given coordinates for 4 distinct locations: a historical park interior, a standard residential street, a major university building interior, and an underwater coral reef view. They must drag Pegman to each location sequentially, observing his color change each time. The sequence of colors corresponds to a sequence of colored levers or buttons in the physical room. The successful sequence is determined by assigning numerical values to the Pegman states: yellow, 1, green, 2, blue, 3, and a rare orange state, 4, often signifying user-submitted photospheres. If the sequence observed is green, blue, yellow, orange, the code is 2314. But there's a twist. The final location, the coral reef, requires the player to navigate to a specific Google Ocean view, where Pegman turns into a dive bubble icon, which represents the number 0. Thus, the real sequence might be green, blue, yellow, dive bubble, resulting in 2310. This incorporates a less used feature, forcing players to think about the environment, not just the avatar's standard palette, and test their knowledge of Google Earth's related features. Business Listing Anomaly exploits the editable, often subtle metadata surrounding local businesses. The team is directed to a listing for a seemingly innocuous business, perhaps a fictional Atlas locksmith. The crucial clue is hidden in the operational hours. Most hours are standard, but one day shows an unusually precise closing time, for example, Friday, 10:47 p.m. The numbers 1047 are the first 4 digits of the combination. This requires the players to not just glance at the listing, but meticulously cross-reference all available data fields for any non-standard entries, rewarding careful inspection of the mundane details inherent in the Maps interface. The business listing puzzle continues by utilizing user-generated content, the reviews. The team must locate a specific, highly detailed review left by a fictional account, say Cartographer Chris. This review is unusually long and descriptive, but hidden within the prose are capitalized letters or specific punctuation marks that form an acrostic code. For instance, the first capitalized letter of every sentence might spell Key East. This is the directional sequence needed for a directional padlock: east, east, north, east. This requires deep reading and parsing of what seems like irrelevant community feedback, transforming user comments into crucial instructional metadata for the escape room. The satellite image filter puzzle requires understanding that satellite imagery is often composite and can be manipulated digitally. The puzzle starts by presenting coordinates for a remote, flat expanse of land. When viewed with the standard satellite layer, nothing is unusual. However, the physical clue indicates that a false color infrared filter must be applied. In the escape room context, this is achieved by instructing players to utilize a third-party image manipulation tool on a screenshot of the location. Applying the filter reveals a large, previously invisible message, perhaps painted in special reflective paint, visible only in the infrared spectrum. This message is usually a large 5-digit number painted onto the field. The solution found in the filtered image, say the number 71920, is not the final key, but rather the grid coordinates for the next clue. The players are then directed to a different location on the map, a dense urban area this time. They must overlay a pre-provided physical grid transparency onto a printed satellite image of the urban block. Using the digital coordinates, 7, 19, 20, they must locate 3 specific intersections on the grid. At those 3 points, they identify 3 minor symbols visible only in the high-resolution satellite view: a specific tree shape, a unique car parked, or a colored tarp. These 3 symbols correspond to 3 physical keys in the room. This puzzle leverages the measure distance tool with extreme precision. The team is tasked with finding the shortest possible path between 2 highly specific, distinct points: the corner of a fence post at a famous park and the exact center of a specific monument's footprint. The catch is that the measurement must adhere to a non-standard rule. For example, walk only on grass and ignore all paved paths and bridges. This forces the players to meticulously use the distance tool's multi-point drawing feature, ensuring they trace a custom, serpentine path that bypasses default routing algorithms. The distance must be calculated to 3 decimal places. If the precise measured distance is, for instance, 4.712 kilometers, the required combination is 4712. To ensure accuracy, the escape room uses verification. The players must submit the coordinates of the 2 key turning points along their custom path into a digital interface. If the distance generated by the path connecting their submitted points matches the solution's distance to within 5 meters, the 4-digit code is revealed. This enforces methodical verification of the player's non-standard routing, proving they didn't just stumble upon the correct distance, but actively built the path according to the constraints. Drawing inspiration from GeoGuessr, the Missing Landmark Challenge requires visual deduction. Players are given a highly obscured street view image. Perhaps the main signs are blurred, and only partial street markings and specific architectural elements are visible. The team must use context clues, like common utility pole designs, national-specific traffic lights, unique storefront fonts, or distinct road signs to narrow down the location to a specific city, perhaps even a specific country known for a certain style of paving. This tests broad global geographical knowledge and pattern recognition, eliminating the need for simple search engine reliance. Once the city is successfully identified, the players are instructed to search for a monument related to local history within that area. They must use the map to sweep the city, identifying minor monuments visible in Street View that are not major tourist destinations. Upon locating the correct obscure statue, often dedicated to a local founder or an animal mascot, they must look for a specific inscription, perhaps a date or an object held in the statue's hand. If the statue is holding a quill and the physical room has 5 quills, the code is 5. This final step requires painstaking ground-level digital exploration within a limited, self-identified radius. The transit route cipher leverages the detailed public transportation data Maps contains. The team is given 4 stops, A, B, C, and D, in a major metropolitan area. They are challenged to find the most efficient route that connects all 4 stops, requiring exactly 2 transfers. The actual solution is not the time taken, but the numerical route designations themselves. If the path requires bus route 14, then subway line 3, followed by tram route 72, the numerical code is 14372. This requires switching to the transit layer and carefully mapping the transfers, ensuring they select the routes whose numbers, when concatenated, form a precise 5-digit sequence. Building on the transit system, the team is asked to find a specific piece of time-based metadata. Using the same route they just mapped, they must check the scheduled arrival time of the final vehicle, Tram 72, at the final destination, Stop D, on the next Sunday morning, regardless of the current day. If the arrival time is 08:35 a.m., the solution is 08:35. This relies on the system's ability to forecast schedules days or weeks in advance, rewarding players for understanding that geographical data includes temporal attributes. They must meticulously select the correct date and mode of transport to extract the precise time-based key. The elevation code utilizes the terrain layer and the underlying digital elevation model, DEM data. The team is given coordinates for a specific ridgeline in a mountain range. They must activate the terrain layer to see the contour lines. The puzzle asks, how many major contour lines cross the primary east-west road segment between these two coordinates? Counting the lines reveals a numerical value, say 6. This is the first digit. The challenge here is ensuring they are counting the correct, standardized contour lines and not minor elevation changes, forcing careful reading of the map's legend. The second part requires calculating the precise difference in altitude between two small, non-obvious geographical features, the highest point of a specific, unnamed hill and the surface elevation of a nearby lake. This is achieved by clicking the precise locations on the map and extracting the altitude value displayed in the lower corner of the screen. If the hill is 542 meters high and the lake is 398 meters high, the difference is 144 meters, which forms the last 3 digits of the code. The puzzle tests whether players know how to extract the raw DEM data directly from the user interface, a feature hidden in simple point clicks. Custom Marker Sequence leverages Google's My Maps feature, which allows users to create and share custom layers of geographical data. The team is given a link to a shared custom map populated with many confusing, unlabeled markers. The physical room contains a coded message that can only be decrypted using a color sequence. The players must click on the markers in a specific chronological order, perhaps listed by creation date in the sidebar, to reveal the hidden color codes embedded within the description of each marker. For example, marker 1 equals red, marker 2 equals blue, leading to a sequence lock based on colored buttons. Within the description box of the final marker on the custom map, a crucial piece of text is hidden. It might be a detailed history of a fictional character named Mr. X. Tucked deep within this text is a seemingly innocuous piece of information, such as the character's birthday, 04/17/1988. The sequence 41788 is the 5-digit combination needed for a safe. This puzzle reinforces the idea that geographical data is not limited to geometry and topography. It often includes rich, narrative metadata that must be thoroughly extracted and deciphered from the user-generated text fields associated with custom pins. The rating star cipher utilizes the average star rating of specific businesses. The team is tasked with finding 3 distinct but related businesses, e.g., 3 rival coffee shops. They must calculate their combined, precise average rating. For example, Shop A is 4.3, Shop B is 3.1, and Shop C is 4.7. The total is 12.1. The code is the decimal portion multiplied by 100, 121. This requires accurately recording the live, dynamically changing rating score, rewarding players for understanding that crowdsourced data is a usable, albeit volatile, form of geographical metadata that contributes to a lot combination. To complete the puzzle, players must find a specific review left on one of the businesses. The puzzle provides a short quote, "The beans tasted faintly of sulfur." The team locates the reviewer who wrote that quote and then uses their publicly available profile data. If the reviewer's profile picture is that of a cat and the physical room has 3 cat figurines, then the number 3 is the final digit. Alternatively, the reviewer's username, such as TangoFox22, might reveal the password Tango for a terminal, linking the persona metadata to the physical escape room narrative and characters. This puzzle requires integrating the specialized addressing system, What 3 Words, which assigns a unique 3-word combination to every 3 by 3 meter square on Earth. The team is given 3 seemingly unrelated words: table, chair, spoon. They must input this into the W3W system to receive the precise geographical coordinates. These coordinates are then plugged into Google Maps. This process tests the player's ability to seamlessly switch between 2 related geographical tools, using one to generate the input for the other, proving they understand coordinate conversion and modern addressing alternatives. The coordinates derived from W3W are the starting point for a tiny, high-precision scavenger hunt. The team must drop Pegman onto the coordinates and look within the 3x3 meter square. Because the location is so specific, they must search meticulously for a tiny clue visible only on the ground. Perhaps the number 8 is faintly etched into the virtual curb directly next to a utility box visible in Street View. This final micro-observation scale, applied to an extremely small area defined by an external system, proves mastery of the digital geographic environment and yields the last digit of the final combination. The preceding 12 unique puzzles force players to interact with Google Maps in 12 distinct ways, moving beyond simple navigation to complex data analysis, calculating coordinates, extracting data from historical layers, reading UI status changes, analyzing business metadata, manipulating imagery filters, and interpreting non-standard routing requirements. The success of the escape room relies on integrating these disparate solutions into a final, unified master key. Perhaps all the single digits found, 8, 5, 2, 7, etc., must be ordered chronologically by the time they were solved to unlock the final safe. This comprehensive challenge proves that global geographical information systems, GIS, are perhaps the most robust and fertile ground available for creating infinitely scalable, intellectually stimulating, and highly accurate escape room experiences. The map is no longer just a static guide. It is a dynamic archive, a repository of community data, and a geometric canvas hiding billions of pieces of metadata waiting to be unlocked. By turning Google Maps into an active puzzle tool, we force ourselves to look beyond the routes and truly appreciate the complexity and engineering that underpin our digital world. This framework is highly scalable. You could run 1,000 variations of this room simply by changing the coordinates, the dates, or the transit routes. We encourage you to use these concepts to challenge your friends, design your own geocaching adventures, or simply explore the hidden depths of digital cartography. Thank you for joining us on this geographical puzzle-solving journey.